Okay, in group 3, we were focusing on what knowledge do engineers need, again from systems engineering. And first of all, again, we were looking at this position that engineers not necessarily looking at systems engineering or the systems engineering methods we might apply or the tools in their engineering. We did have a little discussion about whether somebody does project planning. Should we include that on our list? Because, I mean, if they're doing some sort of project planning. But in some cases, like I just heard with the previous example, that if you really take a systems approach to it, it's not just project planning, it's actually trying to do it a little bit better. So we had some kind of discussion on that kind of discussion on the different aspects we included in there. So again, we were looking at, again, trying to identify all that kind of knowledge at some level, but not get too far with it. The list started to get long for a while there, and then we had to try to cut it back. So, of course, all being systems engineers, it's hard to kind of cut things out of there. You say, no, you want to include it all in there, but then you're realizing that, okay, well, we got to make sure that we're going to make some inroads. So they said, 2 things might not be enough for us. We're trying to get all the knowledge in there, but we try to get a few more of these things, but we realized that we tried to let it emerge how many things came out on the top of the list. Again, the whole idea was to make engineers better engineers. But I do think, though, in this, we were talking about engineers, I think. I think the whole concept was we're looking at engineers in this education. And I do think there's some aspects, like you said, for design or other things. So I think, but we did focus on engineers, I think, in all of our discussions in this. And again, when we say show value, I think we're trying to just cross over to look at how the group, I think it was group 1, did value on this. And again, once it gets into the education and engineers, it's going to help the future employers and, of course, I think the institutions, because if they'll educate students that give employers what they're looking for and all the values that were part of the value proposition that you mentioned in group 1 there. Here's the people we had on our team, and everybody can follow up on that later. Again, we tried at first to at least define an engineer, so we knew what we were talking about from this perspective, and we just said that, again, it's a practitioner concerned with applying that science, knowledge, math, and ingenuity to develop solutions for this technical, societal, and commercial problems and opportunities. Again, we're not wedded to this, but we wanted to get some kind of context for our discussion, and that's what we're talking about here is engineers. And then again, from looking at that whole perspective of things that are going to help benefit society, which is really the primary purpose of engineers. Again, kind of an eye chart, but this was the list we came up with. It certainly wasn't disorganized at first. We came up certain lists and try to harmonize some of our definition, categorize things. We kind of started with a little bit on trying to put things into some kind of categories for affinity here. The category titles didn't stay. This is kind of our first list here. And then what we did is we did some voting. We let everybody take 3 votes, pick your 3 things that you would include on the list, and I forget, we had something like 12 people, I guess, 13 people. So, so again,
voted by category?
No, actually, we do any of the items. So you voted like for your 1A, 1B, 1C, or 2A, B, C, and you pick any of the 3 items at that level. And then this is what we came up with. Was the ones in red there were our top, what is that, 8, I think, things. We just kind of made some kind of cutoff that said, well, if at least something got 2 votes, well, we included in there. So again, we felt like we didn't want to cut everything off the list, but we thought just that small group, figure out what were the things that we thought were most important. And again, this was, again, at the end of the first day. So then the second day we...
Where's 1? I'm sorry.
What's that?
Where's number 1?
No, that's
No, it's not a ranked list. It's category 1.
So,
that you could see that, so anything in red kind of made the top. And we weren't trying to say that, I mean, it got 7 votes, but it just means it made the... Yeah. Yeah, it actually was. I mean, most people, when we're done voting, interdependence and all those aspects there. So again, we started to play around with this on day 2 a little bit and decided that, sort of, give me go back for a second, concept exploration meant kind of the front end thing, and you're trying to figure out what's going on. Is there a problem out there that needs to be solved? Could you do it with blimps or chimps or whatever you wanted to do and figure out what the problem might be? And then eventually you're going to get into designing something. And then you've got some sort of control on the outside, whether it's project controls or configuration management, those kind of things. But then we decided after, well, maybe we'll be a little bit more specific about some of the categories of the titles, and then we broke some things out into what we categorized more as sort of system science and fundamentals, and we kind of pulled that fundamentals word out of the CBOC because System science, I guess when you try to look at that again, it's not quite as defined that we could say that what is that body of system science. So we said, well, it's science and fundamentals. And then change that other part to systems thinking. So instead of that exploration front end, categorized it in those with those titles. Included analysis in the word design in number 3, and then finally at the last one, sort of technical and project management and those kind of controls that go on as far as doing the actual project. And I think the context for all of this was not just engineers, but doing kind of a capstone project. I think some of this could also be in sort of a sophomore level or even a freshman project or something, or even a team that was working on it. But at the time that you write a capstone, this is what we were really thinking they would need in order to improve some of the ways they would approach the engineering process there. And we weren't sure what to call them. We started with different top lists, top 10, top 8. And we said, well, they're the differentiators that would, from a systems perspective, this could differentiate teams that use this as opposed to ones that didn't use these methods and concepts in their approach to developing things with systems. And what we did is since we renamed things and put them in different categories, we said, okay, let's vote again. So everybody, again, this time we each got to pick 5 categories because we were down to 9 people. We lost a few people, so we said we wouldn't quite, we may not get enough if we go with 3 again, so we said, well, okay, everybody could have 5. And then this, again, the ones that are highlighted in red were the top ones that we came out with. Again, this isn't the be-all and end-all list, and we didn't want to cut everything off of there, but we kind of came out with this subset of things. There was some discussion that perhaps at some point it shouldn't be the system engineers sitting in a room deciding what are the most important things, but maybe there's value in having people that even teach mechanical engineering or electrical engineering or other types of things on a particular team be able to say what's important for us in the way we approach this that may make a difference in the outcomes we are trying to generate. So we said, again, this is just one way of looking at what we thought were some of the more, the higher ranking aspects related to systems engineering. And some of the things we had as we kind of broke it down, and you see requirements analysis is on the list there. And you see that requirements elicitation we put as part of the problem analysis, but requirements management didn't make the list. And we figured, well, at this point, really when they're looking at the requirements while you're doing design, you've got to be constantly looking at those, analyzing them, looking at deriving your requirements, looking at allocating requirements, doing that kind of thing. And at the front end, you're really doing elicitation, needs elicitation, working with the stakeholders, trying to understand the problems and their perspective. So again, we tried to break it down to some level of detail, but in some cases we thought it was a little difficult. Things like systems architecture and analysis, I mean, there are entire courses, if not graduate courses and degree programs on those. So the concepts are there, but we've got some further work to do to kind of flesh out, okay, what are the aspects in there that would be the knowledge pieces that you could put in there in some way, shape, or form that would actually add value. And I think that gets down to when you start to deliver things, is there a module on it that would work, or a lecture, or if you want to give somebody at the beginning the whole idea of what is an architecture and you show them some of the pictures. Like if one of the favorite ones I use is I got a Nikon camera, digital camera, and you look at the camera there, you get in the box and maybe it has a cable on it, but it shows that it goes out to the printer, it goes out to the cloud, it goes out to your Wi-Fi, to your phone, to send out to your social media network. So where is the system? What's the boundary? So when you're building an architecture or something like that, you got to take into these things into consideration. So you can start with a high-level picture like that and eventually get into the whole concepts of architectures and views and different types of products and modeling of architectures and things. We also, for instance, on modeling, added system in front of that because we started with modeling, but from my perspective as an engineering student and teaching engineering in many disciplines, modeling is, models are what engineers use to manipulate their perspective of what they're dealing with. So we figured it is really system modeling, and that is what we're talking about. So, but we tried not to put system in front of everything because we could do that again, but so again, try to put it where we thought it would fit. So these are the without any kind of categorization or numbers or voting or anything, these were the topics we came up with. Felt fairly comfortable with the list, but again, is it something that the disciplines would pick or everybody in the room would agree to? Well, probably not, but we're probably close enough. And even going back to a larger list, you can always, again, pull things in from that. It can be one from column A, one from column B, and 3 from column B. You don't have to pick a particular list, but I think we have a pretty good start on at least a first cut at what the top 10 items are with some sort of categorization. One of the follow-on steps we thought might be useful would be to try to get to these knowledge differentiators to a little bit more of a level of detail, and as a way to look at this maybe in Bloom's cognitive domain, saying, in different engineering disciplines, maybe you just want somebody to be able to understand a concept, but they're not really going to apply it to what they're doing, or it's just something they're just aware of while they're working with things, but in some cases you want them to actually apply things. So you want them to analyze requirements. They've got to know how to analyze them. So they actually have to know the definition of them, they have to understand them and analyze them. Some other things might be applied. They might have to actually apply some of the aspects of dealing with some kind of change in their project, and they're going to have to apply methods to actually mitigate some consequences of that, or find out if they can change a requirement, or maybe derive a couple new requirements that'll meet that. So finding out which one of these categories that we've picked, or differentiators that we've picked in these different categories, might apply to the different levels of cognitive abilities that would be expected for a particular project or a particular discipline or a particular team. And I think if once you can get those, these are fairly standard terminology for developing learning objectives that can then be used as the basis for the modules that would cover those. So just some way to start out looking at how to kind of parse this out into the levels that you would cover. And then perhaps going out to other professional societies, or departments or people who teach in these areas, and find out, okay, for these different differentiators, we can tabulate from the chart to sort of infer what's going on there, but maybe for these other societies to find out what they think, first from the cognitive level, or maybe which ones they think would apply to their particular field. And then we'd have a kind of a look at the levels of the knowledge expectation they would have of the students to be able to be able to produce things, as well as from a professional society perspective, let's say, be able to say these are the things that we think are important in development of our types of disciplines and approach to the discipline that have to do with the system. This eventually could work out into, since it's all these societies that meet with ABET to figure out what are the ABET criteria, then also see how many of these in a commonality you could start to say to approach people that might say that, well, we represent systems. Well, try not to put it, like I said, above all that, but it's the part that if people can start to see from their different societal perspectives that this is important to us in addressing systems, find out if that criterion 3 list of A through K actually hits.
So I'll say again,
thing.
map these to ABET criteria. Right?
Yeah, they could also be mapped into that as well. Yeah,
you're right. Exactly.
But still, the ABET criteria eventually have to be manifested in learning objectives that you actually teach and then assess, and then roll up to show how you meet those. But that's that's right. Yeah. So.
Okay. Also, the list of disciplines here are just a notional list.
Yeah.
If you're all inclusive, it'd be too big of a chart. So it's an idea. But if you go to the previous one. So this one we may give out to electrical engineering community and all the professors and faculty and stuff like that to fill this out, and then go ahead, and then we'll tabulate it in the follow-on.
Yeah, and then maybe some guidance from systems engineers to get to understand what those different what do those things mean to them, to try to get some kind of a dialogue on that, and then document it. So. And again, we had other little charts on what we think we might need to do to document some of the definitions and categories in there, but we won't include that there.
Go to your top 10
questions.
again.
I'm sorry?
Your top 10, the one without, right there. So, a big initiative within INCOSE now is to make systems engineering a model-based discipline, right? So, I guess that would be 3C. That's the only one of those that are related to that. Yes? No?
Yeah, well, I think the system modeling in there was, again, if you're doing design and analysis and you're doing it using models, which I think engineers are, very good at, I think, yeah, that's where the actual models would be. But using it as a way of the models for decision making, and that falls under some aspects of architecture, or maybe D for, because you use the models to be able to help decide and make trade-offs and things. So. Yes, we have another. Oh, yeah, Dennis.
I guess my perspective on this is if we're trying to help electrical engineers and civil engineers introduce systems engineering into the classroom for projects and introductory stuff, we don't want to get into SysML. There's a time to dive into SysML, and this is
That's right. There's a time not to. Yes. Yeah. And I agree. Not every certain system modeling tool or methodology is going to be appropriate for a particular discipline.
I'd like to make two comments about the modeling issue. First, we definitely don't restrict this to SysML. I mean, there's other modeling languages and approaches. And the second thing is that it's not just within design that we have in mind. That a lot of the systems thinking, the problem analysis, that you would use models. For most of these, even in the technical and project management, and dealing with change, et cetera. So that orientation, at least from my perspective, applies.
It's embedded.
Yeah, right. But we wanted to specifically call it out somewhere, so we put it in there.
So maybe it could be pulled out into the fundamentals if it's not, or foundations or something that would apply throughout. On your Bloom's taxonomy slide, it's interesting that this raises the subtle question of you want to introduce this, introduce the systems education so that the engineers will have an appreciation of it, which would get them through the first two levels, and then also presumably help them do what they're supposed to be doing in their own discipline better. So that would be more the stealth side, where you would, but they would get further up into the taxonomy. So it's just interesting to bring the taxonomy into it.
Yeah. There's again, because even before you can apply something, you may have to do everything else to the left at times. Okay. Again, thanks everyone.
Any other questions for this group?
Thank you.